Have you ever wondered if everything you see around you is actually happening right now at this very moment? Or if you are living in a temporal illusion created by a fundamental property of the universe that your brain simply isn't wired to understand? This is a question that Neil deGrasse Tyson, one of today's greatest scientific communicators, poses in such a provocative way that it immediately forces us to rethink everything we know about reality. And when you understand what I am going to reveal in the next few minutes about the speed of light, your perception of time, space, and even your own consciousness will never be the same, because there is something so profoundly strange and counterintuitive about how light behaves in the universe that even the most brilliant physicists admit that our human mind will never be able to truly visualize or feel this reality in a visceral level. Imagine that you are looking at the sun right now and you feel the heat on your skin. You naturally assume that you are experiencing the sun as it is now. But the scientific truth is that you are looking at where the sun was exactly 8 minutes and 19 seconds in the past, not because your vision is slow, but because the light emitted by the sun traveled 249 million kilometers through the vacuum of space at a fixed and unchanging speed of approximately 300,000 kilometers per second before finally reaching your eyes. And if you are one of those who love unraveling the mysteries of the cosmos like me, subscribe to the channel because we have many more fascinating scientific revelations to share with you, and I guarantee that each video will blow your mind in ways you can't even imagine. Now, think about this for a deeper moment. When you look at the closest star to our solar system, Proxima Centauri, you are seeing what it looked like 4.2 years ago. When you look at the Andromeda Galaxy on a clear night, you are witnessing photons that began their journey 2.5 million years ago when our hominid ancestors were still learning to use stone tools. Neil deGrasse Tyson often uses a powerful expression to describe this reality. Looking into space is looking into the past. But he goes further to make us question something even more disturbing. If you never see anything in the universe as it really is right now, how can you be absolutely sure that anything you perceive as now really exists that way? This is not just an abstract philosophical curiosity. It is a direct and inevitable consequence of one of the most revolutionary discoveries in the history of science. That the speed of light is an absolute universal constant, unchanging and completely independent of who is measuring it or how it is moving. And here's where things start to get truly strange in a way that challenges every fiber of your human intuition. To understand why the speed of light disrupts our sense of reality in such profound ways, we first need to go back to the late 19th century, a time when physicists believed they were very close to having everything figured out about how the universe worked. Newtonian physics explained the motion of the planets with impressive precision. Maxwell's equations brilliantly described how electricity and magnetism were interconnected, and it seemed that only a few small details were missing to complete the complete puzzle of physical knowledge. But there was a seemingly simple problem that was troubling scientists. How did light actually travel through empty space? At the time, it was believed that all waves needed a medium to propagate, just as sound waves need air or water. And so physicists had postulated the existence of an invisible and intangible substance that permeated the entire universe called luminiferous ether, a kind of cosmic ocean through which light waves surfed. In 1887, two American scientists named Albert Michelson and Edward Morley performed an ingenious and extremely accurate experiment that was supposed to detect the Earth's motion through this ether. The idea was simple. If the Earth is moving through this ether as it orbits the Sun at a speed of approximately 20 miles per second, then the speed of light should look different depending on whether you measure it in the direction of the Earth's motion or perpendicular to it. Just as a swimmer trying to cross a river experiences different resistance swimming against the current versus crossing laterally. They built an incredibly sensitive device called an interferometer that could detect tiny differences in the speed of light in different directions, carried out the experiment with meticulous precision, repeated it several times, and there were different seasons when the Earth was moving in different directions in its orbit, and the result was absolutely baffling. There was no measurable difference. Light traveled at exactly the same speed in all directions, regardless of how the Earth was moving. This result was so unexpected and so incompatible with the physics of the time that many scientists initially thought there must be some experimental error. But Michelson and Morley were extraordinarily careful experimenters, and their measurements were sound. The luminiferous ether simply did not exist. Or if it did, the Earth was not moving through it in any detectable way. And the light maintained its constant speed in a way that defied all intuitive logic. For nearly 2 decades, this result remained one of the greatest unsolved puzzles in physics, a nagging anomaly that didn't fit into any existing theory, until in 1955, a young physicist working in a patent office in Bern, Switzerland, published a paper that would forever change our fundamental understanding of space, time, and reality. Albert Einstein, then 26 years old, proposed something that seemed completely absurd at first glance. He suggested that we should simply accept the result of the Michelson-Morley experiment at face value and construct a whole new physics based on 2 fundamental postulates. Firstly, that the laws of physics are the same in all inertial frames. That is, it doesn't matter whether you are stationary or moving at constant speed. You cannot do any experiment that reveals absolute motion. And secondly, that the speed of light in a vacuum is always exactly the same for all observers, regardless of how they themselves are moving. This second postulate is where things get truly bizarre in a way that Neil deGrasse Tyson loves to emphasize when explaining relativity to the general public. Imagine that you are in a spaceship traveling at 150,000 kilometers per second, exactly half the speed of light, and you shine a flashlight pointing forward in the direction of your motion. Intuitively, you would expect the light from the flashlight to be traveling at 300,000 kilometers per second, relative to the spacecraft plus the 150,000 kilometers per second of the ship's motion, for a total of 450,000 kilometers per second, relative to a stationary external observer. Right? Wrong. Completely wrong. Both you inside the spacecraft and the stationary outside observer will measure exactly the same speed for the flashlight light. 300,000 kilometers per second. Not a kilometer more, not a kilometer less. How is it possible that 2 observers moving at radically different speeds relative to each other measure exactly the same speed for the same ray of light? Einstein's answer was as revolutionary as it was disturbing. Time and space are not absolute. They are relative and deform in precise, predictable ways to ensure that the speed of light remains constant for all observers. This means that the clock inside the spacecraft is literally ticking slower than the outside observer's clock. Not because there is anything wrong with the clock mechanism, but because the fabric of time itself is moving at a different rate. And, simultaneously, the spatial distances along the direction of motion are physically contracted for the moving observer. And this discovery impacted scientists all over the world. And I wonder, where are you watching from now? Comment your city or country. It's amazing to think that we are all connected in this same universe, trying to understand it better. And we are all experiencing time at slightly different rates, depending on how we are moving through the cosmos. To really capture how deeply counterintuitive this is, let's explore a classic thought experiment that Neil deGrasse Tyson and many other physicists love to use. The twin paradox. Imagine 2 identical twin brothers. One of them remains on Earth, while the other boards a spacecraft that can travel at 99% of the speed of light. The spacecraft travels to a distant star, located 50 light-years away, and then returns to Earth. From Earth's point of view, the complete round trip should take approximately 100 years divided by 0.99. That is, just over 100 years. But when the spacecraft returns, the astronaut twin finds that only about 14 years have passed for him. He is still relatively young, while his twin brother, who remained on Earth, has aged more than 100 years and has probably long since passed away. This is not science fiction remains, is a precise and experimentally verified mathematical consequence of Einstein's special relativity. Time actually moves slower for fast-moving objects relative to stationary observers. And this difference is not only noticeable at speeds close to the speed of light, it can be measured even on much smaller scales. In fact, the Global Positioning System satellites, the GPS you use on your cell phone every day, need to have their clocks constantly adjusted because they are moving in orbit at speeds of approximately 14,000 kilometers per hour and experience time at a slightly different rate than Earth. The difference is minuscule, about 38 microseconds per day. But, if left uncorrected, your GPS would accumulate positioning errors of several kilometers in just one day. So you're literally depending on Einstein's relativity working properly every time you use navigation apps to find your way. The speed of light isn't just an abstract theoretical curiosity. It governs fundamental practical aspects of modern technology. But things get even stranger when you consider another implication of the constancy of the speed of light. Simultaneity is relative. Events that one observer sees happening at the same time may happen at different times to another observer moving at a different speed. This means that there is no objective, universal now that works for the entire universe. The concept of the present moment is fundamentally dependent on its frame of reference. Neil deGrasse Tyson often illustrates this with a dramatic scenario. Imagine that an alien in a distant galaxy decides to invade Earth today, but is located 1,000,000 light-years away. For an observer on Earth, that decision event is happening right now in the perspective of a reference frame. But for someone moving toward that galaxy at a significant fraction of the speed of light, that decision event may have happened hundreds of thousands of years ago in their relative past, while for someone moving in the opposite direction, it may still be hundreds of thousands of years away. Of years in the relative future. The universe does not have a synchronized master clock. Each trajectory through space-time has its own unique timeline, and they are all equally valid. Now, let's dive even deeper into why the speed of light has this specific value of approximately 300,000 kilometers per second, and not some other completely different value. The truth is that this specific number is almost arbitrary in a sense. It is simply a result of the units that humans have chosen to measure distance and time, meters and seconds. What really matters is not the number itself, but the fact that there is an absolute maximum cosmic speed in the universe, a fundamental barrier that no object with mass can surpass no matter how much energy you apply. And here's something that many people don't understand correctly. The speed of light isn't really about light specifically. It's about the fundamental structure of space-time. Light travels at this speed because photons have no mass at rest, and anything massless must travel at exactly the maximum cosmic speed when moving through space-time. Other massless particles, like hypothetical gravitons, would also travel at exactly the same speed. It is more accurate to think of it as the speed of causality, or the speed of information. It represents how quickly cause and effect can propagate through the universe. No information, no signal, no influence can travel faster than this. And this limitation has profound consequences for the structure of reality. One of the most fascinating and disturbing consequences is that this speed limitation creates horizons of causality. There are parts of the universe that are so far away that light from them will never reach us, because the space between us and them is expanding faster than light can travel through it. Due to the accelerating expansion of the universe, there are galaxies that we can see now whose images are gradually fading from view, and eventually, in a few trillion years, future civilizations in our galaxy will look up into the night sky and see only the stars of our own local galaxy. All the rest of the universe will have receded beyond the observable cosmological horizon. They will have no evidence that billions of other galaxies exist or have ever existed. The finite speed of light, combined with the expansion of space, creates a bubble of observability beyond which the universe remains permanently inaccessible. Not just practically inaccessible, but fundamentally and irrevocably inaccessible by the laws of physics themselves. Can you imagine the cosmic loneliness of, and be trapped in an archipelago of stars, surrounded by an ocean of impassable space, knowing that there are entire universes of galaxies that you can never see, reach, or even detect? But perhaps the most profoundly counterintuitive aspect of the speed of light is how it relates to the equivalence between mass and energy, expressed in the most famous equation in physics, E equals mc squared, where E is energy, m is mass, and c is the speed of light. This equation tells us that mass and energy are fundamentally the same thing. They are interchangeable forms of the same physical entity, and the speed of light is the conversion factor between them. But note that the speed of light is squared in this equation, which means that even a tiny amount of mass corresponds to an absolutely enormous amount of energy. 1 kilogram of matter, if it could be completely converted into energy, would release approximately 90 quadrillion joules, equivalent to about 21 megatons of TNT explosion, more powerful than the largest nuclear bombs ever detonated. This is the reason why the sun can shine so brightly for billions of years. It is constantly converting mass to energy through nuclear fusion in its core, losing approximately 4 million tons of mass every second. But this loss is so small, compared to the total solar mass, that the sun can continue this process for another 5 billion years. The speed of light squared is so gigantic that it makes mass an incredibly concentrated and compact way of storing energy, which is why it is impossible to accelerate any object with mass to the speed of light. As you accelerate an object, its kinetic energy increases, but according to relativity, this additional energy manifests as relativistic mass increase. The faster you go, the harder it becomes to accelerate further, because you are effectively getting more massive. And as you get closer to the speed of light, the amount of energy necessary to accelerate you further grow towards infinity. You would need infinite energy to actually reach the speed of light with any mass, and infinite energy simply doesn't exist in the finite universe. So the speed of light isn't just an arbitrary speed limit. It's a fundamental barrier inscribed in the very mathematics of space-time and energy. It's like a mathematical asymptote that you can approach indefinitely but never actually touch. Neil deGrasse Tyson often points out another fascinating implication of the finite speed of light that most people don't consider. When you look at anything around you, even objects in your living room, you are technically seeing the past, not the present. Light reflected from a book on your shelf 3 meters away takes approximately 10 nanoseconds to reach your eyes, so you are seeing the book as it was 10 billionths of a second in the past. Of course, this difference is completely imperceptible on a human scale, but the principle is the same whether looking at a book or looking at a distant galaxy. You never see anything in the universe as it is now. You always see it as it was when the light left that object. This creates a kind of fundamental perceptual illusion. Your brain builds a model of reality based on information that is intrinsically outdated. And the further away something is, the more outdated the information is. But here's the real kicker that challenges our intuition profoundly. There is no objective way to synchronize clocks at different locations in the universe in a way that all observers agree on. Different observers in relative motion will disagree about which distant events are happening simultaneously. So not only are you always seeing the past, but there is no single objective past that everyone agrees on. The concept of now fragments into an infinite number of relative nows depending on your state of motion, and each of them is equally physically valid. This is why some physicists argue that the past, present, and future are not truly distinct, but rather that all moments of time exist simultaneously in a four-dimensional block of space-time called eternalism, or block universe, where what we perceive as the passage of time is just our consciousness navigating through different slices of this block. Of course, this raises deeply disturbing philosophical questions about free will, determinism, and the nature of consciousness that go far beyond pure physics. If all these discoveries blew your mind as much as mine, leave your like, subscribe to the channel, and turn on notifications because we have many more mysteries of the universe to unravel together. And each time you ID is a journey to expand your understanding of reality in ways you never imagined possible. But let's explore even more deeply why our human minds simply weren't programmed by evolution to intuitively understand relativity and the constancy of the speed of light. Our ancestors evolved in an environment where the fastest speeds they encountered were animals running, perhaps reaching 60 or 70 kilometers per hour at most. At this speed scale, relativistic effects are completely imperceptible, less than billionths of a percent. Our brains have developed intuitions about time and space that assume they are absolute and universal. Because this approximation works perfectly well for surviving on the African savannas or escaping predators, there has never been evolutionary pressure to develop intuition about what happens when you travel at 99% the speed of light, because this has never happened in the evolutionary history of any organism on Earth. So when physicists like Einstein tell us that time slows down and space contracts at high speeds, our brains simply don't have the neural structures built in to visualize or feel this as real in the same visceral way that we can visualize and feel falling objects or bouncing balls. This doesn't mean that relativity isn't real. It just means that reality is stranger than our everyday experience has prepared our intuition to deal with. In fact, if you could somehow create a human being who grew up experiencing only relativistic speeds close to that of light, that person would develop completely different intuitions about time and space. To him, time dilation and spatial contraction would seem perfectly normal and obvious, and it would be low-speed Newtonian physics that would seem strange and counterintuitive. Our sense that relativity is bizarre says more about the limitations of our evolved experience than about the fundamental nature of reality. Neil deGrasse Tyson often uses this perspective to remind us to maintain epistemic humility. Our intuitions are not reliable guides to how the universe actually works on scales very different from those on which we evolved, from the submicroscopic quantum to the intergalactic cosmological. There is also a fascinating question about what exactly happens from the perspective of a photon of light traveling at the speed of light. If you could somehow travel along with a ray of light, what would you experience? The answer is simultaneously profound and frustrating. According to the mathematics of relativity, if you were traveling at exactly the speed of light, from your point of view, time would stop completely, and all distances in the direction of your motion would contract to exactly zero. This means that, from a photon's perspective, it is emitted and absorbed at the same instant, whether it has traveled a centimeter or billions of light-years across the universe. From the photon's point of view, the emission event and the absorption event happen simultaneously, with no time elapsed in between. All spatial distances in the direction of its movement have completely disappeared. The entire universe in the line of its path is compressed to a single dimensionless point. In a sense, a photon does not experience time or space the way we do. It exists in a kind of timeless, spaceless eternity. Of course, this is just a mathematical extrapolation, because it is physically impossible for any real observer to actually travel at exactly the speed of light. The Lorentz transformation equations that describe how time and space transform between different frames of reference become mathematically undefined when the relative speed is exactly equal to the speed of light, involving division by zero. So technically, there is no valid photon rest frame in special relativity, but we can calculate what happens as you get closer and closer to the speed of light, and see that in the limit, time goes to zero and distances go to zero. This raises deep philosophical questions about the nature of experience and consciousness. If a photon does not experience elapsed time, does it make sense to say that it exists in the usual temporal sense? Or does he exist in a kind of timeless existence that transcends our normal understanding of being? Let me now introduce another aspect of the speed of light that is often misunderstood even by people familiar with science: the difference between the speed of light in a vacuum and the speed of light in materials. The cosmic maximum fundamental speed of approximately 300,000 kilometers per second is specifically the speed of light in the perfect vacuum of empty space. When light travels through materials such as glass, water, or air, it travels slower, sometimes significantly slower. The reason for this is that photons of light interact with the atoms and molecules in the material. They are absorbed and re-emitted repeatedly as they travel through the substance, and this process of absorption and re-emission takes time, creating an effective delay. The relationship between the speed of light in a vacuum and the speed of light in a material is called the material's index of refraction. For water, the index of refraction is approximately 1.33, meaning that light travels at about 3/4 the speed it would have in a vacuum. For glass, it is typically between 1.5 and 1.9 depending on the type of glass, and some exotic materials can have much higher indices of refraction. Scientists have even managed to slow down light to absurdly low speeds using special techniques in laboratories. In 1999, a team led by physicist Lena Howe managed to slow down light to just 17 meters per second, less than the speed of a cyclist, using an ultra-cold Bose-Einstein condensate. In later experiments, she and other scientists were even able to stop light completely, storing its quantum state in atoms and then recovering it. But it's crucial to understand that even when light is traveling slower through materials, the cosmic maximum fundamental speed hasn't changed. Individual photons still travel at 300,000 kilometers per second between interactions. It's just that frequent interactions with atoms create an average delay. And there's even a fascinating phenomenon called Cherenkov radiation that occurs when charged particles travel through a material faster than the speed of light in that particular material, though still slower than the speed of light in a vacuum. This creates a shock wave of light, analogous to the sonic boom created when something moves faster than the speed of sound in air, and produces a distinctive blue glow that you can see in the cooling water around nuclear reactors. It's a spectacular sight, and a reminder that the speed of light as an absolute barrier specifically refers to speed in a vacuum. Now let's explore one of the most fascinating and least intuitive consequences of the finite speed of light: the concept of the light cone and causality in space-time. Imagine you are at a specific event in space-time. Let's call this moment and place here and now. The finite speed of light divides the rest of the universe into 3 distinct regions in relation to you. First, there is your past light cone, which consists of all the events that could have causally affected you. These are all the places in the universe from which light could have traveled and reached you up until this point. Second, there is your future light cone, which consists of all the events that you could potentially causally affect. It is all the places in the universe that you could reach or send a light signal by some future time. And third, and perhaps strangest, there is a vast region called separated by space, or outside the light cone, that consists of all the events that can neither affect you nor be affected by you because they are too far apart in space and too close together in time for any signal to travel between you, even at the speed of light. For events in this third region, the concept of simultaneity becomes completely undefined and frame-dependent. Some observers will say these events are happening in your past. Others will say they are in your future, and there is no objective fact about which is correct. This light cone structure is fundamental to causality in the universe. It ensures that cause always precedes effect for all observers, no matter how they are moving. Because for event A to cause event B, B must be within A's future light cone. And all observers will agree on this regardless of their frames of reference. The speed of light is not just a speed limit. It is the structure that maintains coherent causality in the universe. Without this universal maximum speed, it would be possible to have causes occurring after their effects in some frames of reference, creating impossible temporal paradoxes. The constancy of the speed of light is literally what keeps the universe from collapsing into causal incoherence. Can you think of any experience in your life where this causal structure became evident in some way? Comment your reflections. I love knowing how you think about these deep questions in physics and philosophy. There are also profound implications of the speed of light for our understanding of gravity. In Einstein's theory of general relativity, which he published in 1915, a decade after special relativity, gravity is no longer a force that acts instantaneously at a distance as Newton thought, but rather a curvature in the fabric of space-time, caused by the presence of mass and energy. And crucially, changes in this curvature propagate through space-time at exactly the speed of light in the form of gravitational waves. If the sun suddenly disappeared right now, the Earth would not feel the loss of gravitational pull instantly. It would continue orbiting normally for exactly 8 minutes and 19 seconds, the same time it takes for the last light from the sun to reach us. And only then would the Earth begin to move in a straight line as the gravitational disturbance finally arrived. This prediction was spectacularly confirmed in 2015 when the LIGO Observatory detected gravitational waves from 2 colliding black holes more than 1 billion light-years away. Directly measuring the speed of these ripples in space-time and confirming that they travel at exactly the speed of light within experimental limits. This detection was so significant that it won the Nobel Prize in Physics just 2 years later in 2017 and opened up a completely new way of observing the universe through gravitational waves instead of electromagnetic light. But the crucial point here is that gravity, like light, propagates at a finite speed, and that speed is the same as the cosmic maximum fundamental speed. It's no coincidence. It's because both photons and gravitons are massless particles, and anything massless must travel at exactly the maximum speed allowed by the structure of spacetime. The speed of light is actually the speed of everything that has no mass. It is the speed of causality itself. Now, you may be wondering, are scientists absolutely certain that nothing can travel faster than light? Or could there be some possibility of getting around this limitation in the future? This is a question that Neil deGrasse Tyson often gets, and his answer is nuanced but clear. Based on everything we understand about physics, the speed of light is an absolute fundamental barrier to movement through normal space. It's not like the sound barrier that can be broken by applying more force. It's a mathematical consequence of the structure of space-time itself. However, there are some interesting caveats. First, the speed of light limits movement through space, but it does not limit how much space itself can expand. During cosmic inflation shortly after the Big Bang, space expanded much faster than light. And even today, there are regions of the universe moving away from us faster than the speed of light due to the accelerated expansion of space. Second, theoretically, concepts such as warp engines or wormholes could effectively allow faster-than-light travel by bending or creating shortcuts in spacetime without actually moving through space faster than light. But these concepts require exotic forms of matter with negative energy density that probably do not exist or are impossible to produce in macroscopic quantities. and may violate other fundamental laws of physics, such as the second law of thermodynamics, or create causal paradoxes. Third, there are strange quantum phenomena, like quantum entanglement, where measurements on entangled particles seem to correlate instantaneously, even at arbitrary distances. But it can be proven mathematically that this cannot be used to transmit information faster than light, so it does not violate causality. The current conclusion is that, although physics allows for some exotic situations where things can appear to move faster than light in technical ways, the speed of light as a limit for information transmission and causality remains inviolate in all well-established physical theories, and any attempt to violate it leads to mathematical contradictions or causal paradoxes. It is a barrier that appears to be absolutely fundamental to the logical coherence of the universe. Perhaps the most deeply philosophical aspect of all this is what it means for our understanding of objective reality. If different observers experience time at different rates, measure different distances, and disagree about simultaneity of events, is there really a single objective reality, or is reality fundamentally subjective and observer-dependent? Relativity's answer is sophisticated. There is an objective reality, but it does not exist in terms of separate three-dimensional space and one-dimensional time, as we intuitively think. Instead, objective reality is a four-dimensional space-time where all events have defined locations, but how you divide that space-time into spatial slices and temporal direction depends on your state of motion. Different observers slice space-time in different ways, but they are all slicing the same underlying objective structure. It's analogous to how different people looking at a cube from different angles see different two-dimensional shapes projected. One sees a square, one sees a rectangle, one sees a parallelogram, but they're all looking at the same objective three-dimensional cube, just from different perspectives. Similarly, different observers in relative motion see different projections of the objective four-dimensional reality of space-time into their subjective three-dimensional spaces and one-dimensional times, but they are all observing the same underlying reality. Neil deGrasse Tyson often emphasizes that relativity does not say that everything is relative in the postmodernist philosophical sense. It says that certain quantities that we naively thought were absolute are actually relative to the observer. But there are other quantities called invariants that all observers agree on, such as the space-time interval between two events or the speed of light in a vacuum. Physics is about discovering those invariants, the objective quantities that transcend individual perspectives. So, the speed of light is paradoxically both what shatters our naive notion of absolute reality and what grounds a deeper understanding of objective reality at a more fundamental level. As we approach the conclusion of this intellectual journey through the implications of the speed of light, it is worth reflecting on how it transforms our experience of being alive and conscious in the universe. Every photon that enters your eyes carries information about past events in distant places. Your vision is literally a time machine that allows you to observe the past of the cosmos, from the billions of years ago of distant galaxies to the nanoseconds behind objects in your living room. Your consciousness is constantly constructing a model of reality based on inevitably outdated information, and there is no way to update that model to the true universal now, because such a thing does not objectively exist. We are all living in our own slightly out-of-date time bubbles, connected but never perfectly synchronized, and there is something deeply humbling about this. Our perception of reality is fundamentally limited not by failures of our senses or brains, but by the laws of physics themselves. There are aspects of reality that are inaccessible to our direct experience not by technological limitation, but by fundamental impossibility. As Neil deGrasse Tyson often reminds us, the universe does not owe us comprehensibility. It was not built to make intuitive sense to evolved apes on a rocky planet orbiting an ordinary star. The fact that we can understand anything about the fundamental laws of the cosmos through mathematics and careful experimentation is extraordinary. The speed of light teaches us that reality is stranger, richer, and more beautiful than our everyday experience suggests, and that our intuition is a wonderful guide for navigating the world on a human scale, but a terrible guide for understanding the cosmos on much larger, much smaller, very fast, or very massive scales. We need mathematics, experiments, and humility to extend our understanding beyond the boundaries of our direct experience. And perhaps the most valuable gift that science gives us is not so much definitive answers as a deep appreciation of mystery, the vastness of what we don't know, and the wonder that the universe allows complex structures like you and me to arise and contemplate their own existence, trying to understand the laws that govern us. When you look up at the night sky and see starlight that has traveled years or centuries or millions of years to reach your eyes, you are participating in a cosmic connection across time and space, mediated by photons that experience no time or distance from their own perspective, connecting you to distant events both spatially and temporally in ways that defy description in everyday language. There is a beauty in this strangeness, a kind of poetry in physics that reminds us that to live means to be steeped in mystery, and that our search for understanding is simultaneously profoundly successful in certain domains and necessarily limited in others. The speed of light delimits both what we can know and what will always remain beyond our reach, and there is a kind of melancholy beauty in recognizing these boundaries. If you have made it this far with me in this in-depth exploration of the speed of light and its perplexing implications for reality, time, space, and consciousness, thank you very much for your attentiveness and intellectual curiosity. You are among those rare individuals who are not content with superficial answers, but want to truly understand the deep nature of reality, even when it challenges us. For your most basic intuition, leave in the comments which part of this journey impacted you the most, which concept was hardest to internalize, or which question lingers in your mind, and share this video with friends who also love deep science and natural philosophy. Together, we can build a community of people fascinated by the cosmos and dedicated to understanding it better, one counterintuitive concept at a time.